A binary search, on the other hand, works only if the list is already sorted. It's a recursive method, and it starts by selecting the middle item from the list. If there is no middle item, it'll choose randomly, or it might always choose the lower one or the higher one. Doesn't really matter which. So in this case, let's assume we're still looking for the number 64. Binary search starts by selecting the middle value, which in this case might be 59 or 60. It compares that number to the number we're looking at, and it returns one of three results. It's higher, it's lower, or it's the right number. If it's the right number, we stop. We found it, and we return the index of that value. If the number is higher, though, then we know that the number we're looking for must appear in the first half of the list. Here, though, it's the opposite. 59 is lower than 64. So we know that not only is 64 not located here, but it's not located anywhere in this entire half of the list. 64 is greater than 59, and so it must occur later than 59. So in one big swoop, we've gotten rid of half of the numbers. That's already much more efficient than the linear search. But then we recursively call the binary search on the remaining list. So with the remaining portion of the list, we again grab the middle number and we compare it. Now 83 is greater than 64. So now not only do we reject 83, but we reject every number after it. So we again grab the middle number, compare it. 70 is greater than 64, so we reject 70 and all the numbers greater than it. And now we grab the middle number again. 64 is equal to 64, and so we're done. We found the number. So in this case, it only took us 4 guesses to find the right number. We guessed 59, 83, 70, and then 64. Our worst case scenario in this case, where we have 64 numbers, would have been 6. If we'd been looking for 65, for example, instead of 64, then after checking against 64, we would have erased that part of the list. Then we would have checked 68, erased that part of the list, and that would leave us only our value. So as you can see, the efficiency of a binary search is far higher. It actually runs in O of log n. Doubling the number of items only requires one additional operation, because each operation throws out half the items in the list. It took 6 operations to find a number out of a list of 64. But it would only take 17 operations if you were finding a number between 1 and 100,000. If you were finding a number between 1 and a billion, it would only take 30 operations. So it takes 6 operations if we're finding a number among 64, but only 5 times as many operations if the size of our list expands by a factor of 500 million. So binary search is extremely efficient.